Welcome to the 820. Welcome. This week I'm going to cover electrical optical crystals and polarization. I'm just getting back from vacation, trying to get caught up with work and life and everything. So this rotating crystal is an octahedron, which is the shape of lithium niobate crystals, roughly, that I've learned. So that was one thing I learned in the last couple of weeks. So we'll be talking about octahedron is the shape. I was curious about X, Y, and Z axis. I learned a little bit about that. The Z axis of a crystal is generally the axis where the light is flowing through the crystal, and the X axis of a crystal is generally the widest part, and in the case of lithium niobate, it's the horizontal or the flat line. And then this was generated by ChatGPT. It's a terrible octahedron. As you can see, it's got many more surfaces. But I looked at my color chip transceiver and ripped it apart this last week. This is the end the fiber optics go to. There's a fiber optic in and out, and this is the electrical side. So this device converts light to electricity and vice versa. At the top, you see a crystal. I'm 90% sure that is a lithium niobate crystal there. And my intent at first was to rip this thing out and run laser signals through it. I may still do so, but at the moment I'm hesitant to take this thing apart. It's a beautiful feat of engineering. It's so tiny, and it does so much. On the top is the laser, I believe, going out, and on the bottom here is the light coming in. This is a crystal I bought from China. I was trying to figure out what it said on the box. And again, Google Translate is your friend. So this is product W, and I believe I did not want product W. This is a 10 by 10 by half a millimeter crystal, lithium niobate, cut on the z-axis. You can see it there. And so the thickness of this crystal, I believe, is the z-axis. Or actually, it may be cut on the z-axis. Yeah. So anyway, what I wanted was this long rectangle you see at the bottom of or these little rectangles on the left. That's the shape I wanted to replace in this box here on the pad. This is where the electrical optical crystal goes in the system I'm trying to create here to experiment. And so I'm still going to have to buy some more crystal. I've been working with my polarizers. They did come in. I ordered them from Amazon, and I think it was Alibaba, or at any rate, Chinese website kind of thing. And that was kind of wonky. I did find Edmund Scientific or Edmund Optical has these polarizer sheets for $15 each, and I've ordered some more because I ripped into mine and broke them. But I've got some video coming up showing me working with electrical optical crystals, so we'll be watching that here in a second. But effectively, I've got a polarizer and then a quarter wave that circularly polarizes.
We have both lights lit, so I've got the prism set up right. I put polarizing film in front of the light. I can suppress the blue light. If I rotate it 90 degrees, I can suppress the other light, which is just what it should have done, because the prism is forwarding one polarization of the light to one detector and another polarization to the other detector. Blue light out, blue light on. Blue light out, blue light on. Okay, so now this is a polarizer. It doesn't have any markings on it that I could see. Tell me what direction is what. Now I'm going to try this other film. If it's circularly polarized, then it's doing the same thing, right? Yeah, it's the same kind of film. Oh.
So if it was circularly polarizing, both lights would always stay on. And what I was seeing is rotating this film, I'd turn on one or the other, just like a parallel polarizer. So it wasn't working as here. I'm just taking the circular sheet and rotating it. I'm expecting both lights to stay on. I'm seeing, for the most part, this circular polarizing sheet is behaving like a parallel polarizer. I couldn't figure that out. So then I took the sheets and pasted them. They had a protective coating, and it turns out the protective coating changed the behavior of the sheets. You're supposed to remove the protective coating on both sides. Then the sheets get kind of sticky, and I stuck them together in different ways to see if I could see something. Here we see me playing with it, and finally I found the answer. The circular sheet is a small rectangle in the center, and the big square is a parallel sheet. And as I rotate the sheet, the LCD monitor is linearly polarized, so as I get the right axis 90 degrees, it'll block all light. But if the circular sheet is towards the monitor, it'll change that linear polarizing sheet. So if you flip it one direction and you have the light going to one sheet first, it matters. So which sheet is facing the original light, and you rotate this, you get different behaviors if it's rotated one way. Anyway, I got circular to work playing this experiment with my camera, figuring it out, and I do have, so here we have the linear light is being blocked. So the big sheet is facing the monitor, and so it'll block all light when you rotate it. But if you flip it and turn it the other way, then the circular sheet will convert some of that linear light to from vertical to horizontal or whatever's missing, and you get both. It's pretty cool.
Okay, so it has two different pieces, and I've cut it down so it's easy to handle. But you can see, maybe you can see it. It's got a little angle on it. There we go. So this orientation, I'm getting both. It's not, it appears to be circularly polarizing the light. So what I should get, if I could make a different circuit, which is the next plan, I need to be able to measure the current coming from both optical detectors, and they should be roughly the same in this orientation, because what's happening here, excuse me, with the filters is I'm taking the coherent laser light, linearly polarizing it, so I'm excluding all other x-axis, let's say the x-axis, so all the y-axis data is gone, or the y-axis energy. So I only have x-axis energy, and then I circularly polarize it, which I'm assuming, I am not doing the math on this, but I'm assuming that is going to give me an equal distribution of x and y polarization. And so with that, since I have equal amounts of x and y, if I put an electrical optical crystal in this space right here, then any voltage applied to that crystal will adjust and squeeze that circular to make it an ellipse, and then I can measure the voltage. I can measure the change in the polarization and measure the change in the voltage.
Φως ταχύτητα. Φως ταχύτητα.